All right. So new chapter 10 in the book, the introduction to simulation. We're talking about computer-based simulation. So most of the models, actually all the models that we talked about in optimization, they were deterministics. What that means is our inputs that we put into our model were determined. That means they were certain. We were certain that they were the data that we know they are. But generally, that's not the case. So we are facing uncertainty in almost all aspects of life, including the data that we get from the systems, because the systems themselves, they are not certain. They're stochastic, so they can change. They can be stochastic. They can produce randomness in the output. So their output is going to be, for example, our input. So our input is going to be uncertain as well. So this is what we want to talk about specifically in this course: simulation, studying simulation as an approach for dealing with uncertainty or probabilistic or stochasticity in the system. Okay, so we're going to talk about the Monte Carlo simulation, which is a kind of a static simulation. We have other types of simulation, such as the dynamic, which is beyond the scope of this course. So we're going to only talk about Monte Carlo simulation, which is just using random samples to deal with the system uncertainty. And so let's get started. You need to refresh a little bit your memory of the statistics courses that you have taken. Not too much, though, don't worry. Right, so the goal of computer simulation to estimate the real system's behavior, or to study the system's behavior, which for some reason we might not be able to do, or it's too costly, or it's too generous, or whatever reason. Okay, so for example, we want to estimate the average mu and the sigma, the standard deviation of a performance measure. We can look at the whole distribution of performance measure of any specific percentile of the system as well, instead of like having the whole distribution. So it could be 90 percentile, for example. Find the 19th percentile of the waiting time distribution for, say, a queue system or a waiting line for a Starbucks or restaurant, whatever. Designing systems before it becomes operational. Suppose that we want to design a new system, a new product, or a new service. So before we do that, we kind of simulate that. How would that happen? What would be the impact? What would be the dynamic without having to build it and spend all that much energy and time and money? We just simulate it, which is going to be most effective and more economical, right? Predicting how a system will behave after it has changed. So that's also before and after a dynamic in the system. Okay, for example, what happens to service if demand rises by 50%? Okay? So we can kind of find a threshold of stress threshold of a system, right? With the fluctuation in the system, right? And of course, visualizing the system is going to help us to better understand the model for the system. So generally, we can say the benefit of computer simulation are they are cheaper, they are faster to experiment with the model, with the simulation model, than with the real system. Of course, when you want to, for example, build a new product, for example, if you just do a simulation of that and before you're designing it, it's going to be much cheaper than, you just go ahead and produce the product or provide the service and so design the service to see, how would that turn out in reality. So it's cheaper and also it's faster. Of course, again, just run a simulation a couple of hours at most than just build a new system, which is going to cost you a lot of time and a lot of money. They are easier and more convenient than making changes to the real system, of course. They are less risky. in case of an extreme example is in case of designing a safe car or examining the safety of cars or any other vehicles. You don't want to put a real human in them and to crash them to see, how safe they are, right? So sensitivity analysis can be done, giving us the ability to test a wide variety of scenarios, possible scenarios. All right, so one difference that we have in simulation models and the simulation approach that we do not optimize things here. So there are some tools that they do that, but simulation generally are not optimization approaches. So they're not optimizing, finding the minimum or the maximum state of the system. So they're just studying the behavior of a system given certain parameters in the system. A few applications of simulation. Business operations such as call center staffing. You want to see how many phone agents you would need before you hire them randomly and try, and later fire them. Facility layout. You want to see, what would be the effective and efficient facility layout for your manufacturing site, for example. There should be different departments, the building department, the painting department, the designing department, the quality control department, or other manufacturing departments. Where should they be so that they make the smooth flow of product and information and people and material? Risk analysis. What's the probability of a project losing money? We can have it in different environments, such as healthcare. For example, a good example, we have been through this viral disease for the past 2 or 3 years now. So that's one thing that they can do. You can use computer simulation to study the spread of disease in human societies. So that's very good actually to understand how to get control over this is the spread, how we can actually control it. What would be the best approach without having to shut down everything in our economy? Organ supply and demand, how to allocate kidneys to patients. Hopefully none of us would go through that, but that's actually a big problem that simulation can be helpful for, because again, all of these are happening under uncertainties, and there is no deterministic way to approach this. So you have to be either there are actually uncertainty in the demand for organs and also uncertainty for providers of these organs. Emergency vehicles, we kind of talked about this as a version of this in optimization, where should we locate facilities, for example, police stations or fire stations or ambulances. Okay, so that's that was under deterministic scenarios, but as you know, we don't know when an accident happened, when someone needs to need an ambulance. So so assuming that it's deterministic is kind of not practical. So simulation, using simulation and considering the uncertainty of system, it would be make it the decision more realistic. Or another environment would be the government or transportation. Street cleaning. How do parked cars affect the cleaning in, for example, New York City or even on campus? You see that. For example, if you have been on campus, there are area where you cannot park on the second and fourth Monday from 8 a.m. to 11 a.m. But some people are still park there. Traffic planning, and also because we don't know how many people are driving, at what time, at what is their destination, what is the origin. So that's also a good example of an uncertain system. Okay? So at any given time, you look at the traffic in the outside in a random avenue streets or highway, you see just chaos and uncertainty. There is always this dynamic, uncertain dynamic that goes on. A different number of cars, different type of cars, different people just driving. And another example is airport planning. So, for example, how to position a new runway in a given airport, say Pittsburgh or SFO. All right. So, how we can simulate? How the process is done? Okay, so, studying uncertainty is with data again, but the data we assume that it is random. That means that, okay, there is a source of uncertainty in the system that produces the randomness in the system or stochasticity in the system. Again, we're going to kind of study that to see, based on our statistic knowledge, what kind of distribution it is. Is it normal, for example, distribution? Is it exponential distribution, Poisson distribution, so on and so forth. So, for example, we're going to get data for hourly product demand or time to serve a customer or whatever else parameters as you want to study for the system. Then we develop, based on our observation and based on our knowledge of the system that we gather, we develop probability distribution for the random source or the random event or the random variable from the system. After we have the probability, after we have the randomness kind of take care of, we build a model. Okay, so we create a model. The model is just going to be a sequence of events or a process that simulate or mimics the real system. And then we're gonna run the model with the random data that we have generated or gathered, and then we use probability and statistics to come up with analysis to measure the system output or to study, get an understanding of the system. For example, determine what simulated events occur, track the performance measures, whatever they are, average, standard deviation, variation, mode, whatever else. And run the model for a sufficiently long time, again, because we are working with sample of data. If you remember from statistics, the sample size is important on the certainty that you can talk about, what confident that you can talk about, for example, for the confidence interval. So the confidence, your confidence interval, or the confidence that you have in your outputs, your performance measure, depends on the size of the sample. So you're going to have to run the simulated model for a good amount of time to be able to get those outputs. Probability and statistics, we talk about them, so that's they play key roles. The input for our system, most systems have some source of uncertainty, so that's the random variable that we talked about. We model the inputs, including the probability distribution that we gather from the data and our knowledge of statistics. For example, suppose service time for a restaurant or for a coffee shop, how to represent in the model the service time. So we're gonna estimate that source of uncertainty. That means at the time that someone walks into a restaurant and we actually serve them, not the entrance. That's Poisson distribution. So the service time, that means, for example, so as there are queues waiting in line to get, say, coffee or drinks or whatever at a coffee shop. Each one of them, they want different drinks. We don't know. We can estimate based on historical data, but we are not sure. So our service time, say whatever they want, espresso, coffee, Americano, whatever they want, each time they want to produce that, it's not exactly going to be, a given constant time period. It's going to take a little bit off, a little bit more or less time. So that's also going to be stochastic, right? So, but that's a sort of uncertainty that we can study. We can actually come up with a probability distribution for the service time. So it's like kind of exponential, as you see here. It's skewed toward the right side. I mean, most of the time, say it's 2 minutes, but sometimes it's 3 minutes, and like few times it has been 5 minutes, for example, right? And we put these as input to our model, and the model is going to generate the output for us, which are interested to know. So each model has to be run to produce the outputs for us. a couple of times or many times to produce lots of outputs and then use the statistics to study them, like take the average of them, take the standard deviation of them, and produce confidence intervals or a distribution for them. For example, customer flow time wants the 95% confidence interval for the average of service time. And that's, say, it's kind of like a bell-shaped normal distribution like this, just an example. So again, we gather the data, we kind of come up with the source of the, based on the source of uncertainty, we come up with the distribution or probability distribution for the system, the source of uncertainty or the random variable, and then we build the model, we run the model, we give the input to the model, and we run a couple of times, multiple times, and then we produce the outputs that you're interested in using statistics. So we talked about the statistics and probability distribution. Again, you might need to refresh your memory from statistics courses that you had taken before. So these are the common distribution that we have in statistics. For the continuous, you have heard about normal distribution, or the bell curve distribution is a continuous distribution, and it's like bell-shaped, as you can see here, with an average of mu and a standard deviation of sigma. So these are the parameters of the system we don't really know, so we have to actually estimate them using samples. So it's going to estimate mu, estimate standard deviation. An example of discrete distribution, we have binomial distribution with two parameters, n, the number of replication, and pi, probability of success. So that's discrete. That means, okay, the number for this is discrete. It just has to be a whole number. It's either 0, 1, 2, 3, integer numbers. Another example of continuous, and also we have it for discrete as well, it's the uniform distribution. So the uniform distribution, it has, as it says, the name says, it has the same level of probability or the same likelihood for every possible outcome. So for example, the uniform distribution for A and B, A is the minimum possibility and B is the maximum possibility, and any value between A and B has the same chance here, and the probability that's given, I can see here. It's kind of called also rectangular distribution. So this is A, this is B, and the height of this is 1 over B minus A. So actually the integral of this from A to B is going to give us the whole probability possibility, which is 1, and that would be B minus A. This actually edge here, B minus A, that's the length of the rectangle, multiplied by its height. It's going to give us actually the area of the rectangle here, which is actually 1, which is equal to the probability of, if you find the summation of the whole probability, which is here, because it's continuous, it's going to be integral. So integral from A to B, f of x d of x, which f of x here is 1 over b minus I, going to be 1. For the discrete version, we have also uniform distribution for A to B, but can't be the minimum value, again, possible value is A, the maximum possible value is B, but between A and B, only the integer numbers can occur. For example, A plus 1, A plus 2 until B. We can't have continuous decimal point number here. Right? Another example for continuous distribution is this triangle distribution, as the triangular distribution. So it's like a triangle, as you see here. So this is A, this is B, and M is where this breakage happened between these two, or so it has 3 parameters here, A and B. Depending on where B is, if A actually is equal to kind of the length of these the two foots or legs of this triangle, if are equal, it's going to kind of mimics the normal distribution. For the discrete distribution, we have the Poisson distribution, as you can see here. It has 1 parameter lambda. Another example of continuous distribution, we have the exponential distribution with an average of mu here. So for different values of mu, the shape of distribution is going to change. And for discrete or also for continuous, we can have empirical distribution. That means it's like general discrete values that it's just not any of these. Okay, so it is empirical. So we can see example of these later on. Okay, so another aspect or characteristics of distributions here are whether they are symmetric or skewed. So an example of symmetric is the normal distribution, as you can see here. So if you consider the middle of this distribution, which is the average mu, the left leg and the right leg, the right part, they are exactly mirrored to each other, okay, because they are symmetric. Okay? So we also have a skewed distribution. Skewed, that means that okay, the probability on the left side and right side of the middle is not the same. For example, the exponential distribution, the triangular distribution with a is not equal to the two leg or not. So as you see here, this is kind of skewed towards the b, skewed toward the right. This can be symmetric depending on how you look at the average. Actually, depending on whether you pick the average, which is b plus a divided by 2. So if you consider the average here, the average is here, b plus a divided by 2, then the left and right side is the same. The Poisson distribution is also skewed. Binomial distribution is also skewed depending on n and p. For larger values, actually, it kind of mimics the shape of the normal distribution. So it kind of approximates to a symmetric instead of skewed. We also have another terms here for characteristics about distribution. Those called whether a distribution is bounded or unbounded. For example, does the random variable have an upper limit? Does it have a cap? Does it have like an upper cap or lower cap? If it doesn't have it, then it's unbounded. If it has a lower cap or an upper cap, then it's actually bounded one side. For example, the uniform distribution from A to B, of course, it's bounded from two sides. So it has the minimum value is A, the maximum value is B. It cannot take any value outside of this, right? So that's bound. So all of these distribution that we talked about and many other distributions that we didn't talk about it here, we can actually sample from them using software, statistics software, including also Excel that has some capability to generate these distributions and mimic them and sample from these. Continuous uniform distribution, let's talk about that. So as you see here, it's first of all, it's continuous. It can take any value between A and B. A is the lower bound, the minimum. B is the upper bound, and for any values it can take between A and B. It's bounded by A and B. So we can actually use Excel to generate samples from this distribution. Using RAND, it can generate a uniform distribution from 0 to 1. Then you can just use a simple formula, which is A plus B minus A multiplied by RAND, and it's going to give you a sample distribution from the uniform A and B. So the average here is B plus A divided by 2. And the standard deviation is B minus A divided by sigma, the square root of 12. So we're not going to study why so. I assume that you know, kind of familiar with these parameters here. Okay. So I talked about the uniform distribution in Excel. RAND RAND is going to generate a uniform distribution from 0 and 1, and then we can, using a simple formula, we can generate any uniform distribution by any A and B. All right, so let's see how we can actually do that, how we can sample off a distribution. So the first step is to generate a continuous uniform distribution. That's going to be a get-go, the uniform distribution. It's going to generate a random number between 0 and 1. And that's actually because every probability is between 0 and 1. We can use that to kind of inversely find the input of a probability distribution given the output. So the output is the probability. So we're going to use actually this output using the rand function, which is a uniform distribution from 0 and 1 in Excel to find that. And then you're going to use the cumulative probability y to inversely find the input for that probability. Say the probability distribution f of x, whatever it is, if it's normal or it's exponential, whatever it is, we first going to produce the probability y using the rand function. It's going to be a value between 0 and 1 randomly, and then using that, we're going to using a formula. So we're going to produce the input of the inverse kind of function of the probability distribution that we are interested in, say f of x exponential normal distribution, given that we know the parameters for that. For example, we know the normal distribution, average, and standard deviation, or we can assume that. So these are the two steps. Okay, so let me give you actually an example to make it easier to understand. So say that we want to have a discrete distribution, and these are our distribution. Okay, we have actually three outputs for this distribution. This is discrete. It can only take values of 1, 2, and 3. So this is kind of one example of the empirical distribution that I talked about. Okay, so you can take a value of 1, 2, and 3. That's all. You cannot take any other values, right? This is the probability distribution. It takes the value of 1. That's probability of 30%. Take the value of 2 by the probability of 50%. So that means that the chance that the value is equal to x, the x is equal to 2 is actually 50%. And it takes value of 3 by 20% chance. Okay? So suppose that we want to generate or sample from this distribution. This is our empirical distribution. Okay, so it can take only 3 values with this probability distribution. So this is what we're going to do. We're going to kind of find the cumulative probability. That's the y value, the probability of x. Okay, so it's going to be a value between 0 and 1. The probability that x is less than or equal to 1, that's going to be 30%. The probability that x is less than or equal to 2, that's going to be the probability that is less than 1 plus is less than 2 as greater than 1. Okay, so that's going to be 30% plus 50%, which is 80%. Kind of it's cumulative, it's adding on, right? Because whatever it's less than 1, it's also less than 2, right? And also for the last one, the probability that x is less than 3, so that's going to be cumulatively the probability that is less than 1, is less than 2, and less than 3. So it's going to add up, it's going to be equal to 1, right? So now we have, this is the cumulative probability. We have 30%, 80%, and 1. And then we're going to use the rand function, the uniform distribution in Excel, to generate a value between 0 and 1. And then based on that, if it's if it's say 20% or 0.2, we say that, okay, 0.2 is less than 0.3. That means that it's going to give us 1. Okay. So if it's, for example, 50% or 60%, it says that, okay, 60% is less than 80% and greater than 30%, then it's going to generate for us 2, right? So we'll say if it's 81%, then say 81% is greater than 80% and is less than 1. So it's going to give us a 3. So this is how it would look like. Okay? The discrete probability distribution. The probability of having 1 is 30%. Probability of having 2 is 50%. The probability of having a 3 is 20%. Okay? So this is just this probability distribution that we have here on the left. Okay? Probability of 1, 30%, 2, 50%, and 3, 20%. We just use the histogram to show it here, graphed it. Then the graph below that shows the cumulative probability distribution for that discrete distribution above. Okay, so the probability of x less than or equal to 1, that's 30%. The probability that x less than is equal to 2, so that would be 1 plus 2, so that's 30% plus 50%, that's 80%. And the probability that is x is less than equal to 3, that's actually 100%, right? So that's 1, which is going to be 30% plus 50% plus 20%. So now, again, we're going to generate random numbers uniformly from 0 to 1 as a y value. That means here, 0 to 1. And then if, say, it's here, we say it's a 3. If it's here, we say it's a 2. If it's here, we say it's a 1. Here we go. So random numbers, say it's here. It's 40, it's 50, say it's 55% or whatever. So 55%, it's gonna give us 2. Okay, that's a sample of it. Suppose that we generate another one, it was like 91, 92, 93, whatever percent. So it's gonna give us, output us 3. Okay? Okay. And so on and so forth. So this is how we can sample from a probability distribution. Here we just tried it with empirical, kind of made up, that we all ourselves we made it up, but we can also do that in a different way, but with a similar manner, similar approach for any other distribution. You can sample from distribution. This is what we want to do. Say I say that the service time at a restaurant follows a normal distribution. I'm just making this up, with an average of 3 minutes and a standard deviation of 2. So I want you to generate some numbers for me from this distribution, right? So this is what I mean by the sampling from a distribution. Okay. Any questions so far?
I think I'm good.
Okay. All right, so I'm gonna open up the Excel file here. The SimBasics, we have, I think, 3 versions on 2 or 3 versions on Island. One is data, the other one is done, the other one I think it's the data table. So for uniform distribution, a continuous uniform distribution between 0 and 1, rand function in Excel, it doesn't get any input, just rand, parentheses open and close. It's going to generate a random number between 0 and 1. It can be any number between 0 and 1, right? Including 0 and 1. For generating or sampling from uniform of min and max, say A and B, you can actually use rand and using this formula. So say you want to generate a random data from min and max, uniform min and max, then this is the formula: mean plus max minus mean multiplied by rand. So this is going to generate a uniform distribution, random number from uniform of A to B, from min to max. If it's discrete, then we can use VLOOKUP and kind of do the same thing that I just did in the previous slide. For normal distribution, we can use the norm.inv, that's norm inverse. And first, we're going to generate the probability, that's the y, probability, random number between 0 and 1. So that's the input. The second and third inputs are the parameters, which we don't have it. We're just going to have to use the estimation for that, the sample estimation for average and standard deviation. So this is going to give us a sample of normal distribution of with an average of mu and standard deviation C. And we can also use the frequency table and histogram to kind of find a histogram for that as well. Right. So if you are using the latest version of the book, it has some add-in software that you can use. I'm not going to go through with them because I don't expect you to have them necessarily, and I don't have it either. Right. So let's go ahead with our Excel. So I'm going to open up the SimBasic here. I can get this to open. Just to get every time. All right, so it has several sheets here or pages here for different distribution. So we're going to start off with the continuous uniform distribution, uniform 0 and 1. So the rand function can actually generate a number between 0 and 1, as I said. Okay, so equal to rand, parentheses open and close, and if you click on it, it's just going to generate a random number, right? So this is a random number. Remember that the rand function is actually a dynamic function. That means that each time that you kind of change the spreadsheet, even in one cell, is going to update it. It's going to trigger again, and it's going to generate a random number. For example, if I click here and I click enter, it's going to generate a new number. Okay.
Professor, we're still seeing your PowerPoint. I'm so sorry.
You don't see the Excel file?
No, we see the PowerPoint still.
Oh, okay. Thank you for letting me know. All right.
Thank you, Professor.
Sure. Thank you for letting me know. All right. So I'm going to go again. As you can see here, there are just different sheets or pages here on my spreadsheet. I've already built this. You can actually, we're going to do different distribution, sample from different distribution, starting off with the uniform distribution of 0 and 1. The formula for that is uniform of 0 and 1. The formula for that is rand. So that's equal to rand, parentheses open and close. When you hit enter, it's going to generate a random number between 0 and 1. Okay? So right now it's like 0.629, whatever. So we want only 3 decimal points there. As I said, the formula is dynamic. So every time you click on it, on that cell, it's going to trigger it and it's going to regenerate a new number. So if I click here, enter, for example, it's going to, you're going to see that I have multiple numbers here. Or at some time, you actually intentionally want this to happen, okay? So if you want intentionally this to happen, on Windows, you can click on F9. See F9, I'm just clicking on F9 and it regenerated new different numbers, random numbers. And all of them, as you see, is between 0 and 1. Okay. On Mac, I'm not sure how exactly you should use, probably use F9. And there is another way that's actually you can go to calculate now. If you click on calculate now and look at the random number that I generated, it's going to regenerate different numbers, okay? You can actually copy and paste this for different rows, and it's going to generate different numbers. Say 11, 20 numbers, right? So you see how I have 20 different random numbers, okay? And then you just click on one of them, it's going to generate whole new numbers or calculate now. All of them is going to be triggered and generate new numbers. Okay. I have to open up my John version to see how many numbers did I generate last time. I think I generated 20, 30, I'm not sure. Let's say here 500. Okay, so we want to, okay, so let's see. Using rand function, generate 500 random numbers between 0 and 1 in column A, row 11 to 510. Number 2, copy and paste this special into the frozen, the second column, column B, and then make a frequency table and histogram for these using the data analysis histogram. So this is what I'm going to do. I'm going to generate 500 numbers, random numbers. So this is going to go from 11 to 510. So if you just drag this down, so now I have 510 random numbers. Okay? I copy that and paste it in the frozen data here. So as you see, when I paste it, it's going to be whole different numbers, right? Because I don't want this to be dynamic. I want it just to be frozen, doesn't change. I'm going to paste it as numbers here, values. When I do that, what happens is now my numbers are not going to change anymore. Okay. I mean, the column B, the frozen, these are not going to change. Even if these change, as you see, my numbers in the B column doesn't change, so it's frozen. Okay? So now I want to build actually the histogram. It's too hot here. All right, so I'm gonna go, let me move this. So I'm gonna go to data tab and then to data analysis here. You must have it under the same category that the solver was, okay? Data analysis. Click on it, and it's gonna have these windows open for you. You're gonna have to scroll down and go to find the histogram here. Histogram. Click on histogram here, and then the input range, put your frozen data, which is from B, for me, it's from B11 to B5. So that's B11 to B510. My bin range is this. And I don't want the labels, the output range. I want them to be here, say. That's D10, or E10, E11, so E11. And I want the charge output. So let's see how it's done. Yeah. Okay, so it generates for us this data and this histogram graph, what is called a histogram graph. Okay. Let me get rid of this. I don't need this. And I want to kind of make these. We can make this thicker. So I'm gonna go with, say, 5%. So as you see here now, they are thicker. Okay. So this is the histogram. On the x-axis, that's the bin. That's the number from between 0 and 0.1, say. Okay. So for example, this is the numbers from 0 and 1. The frequency is about 37. Okay. Numbers from 0.1 to 0.2, the frequency is about 50. numbers from 0.2 to 0.3, the frequency is about 52. So you can see here. Okay? So this is what exactly it has done. We generate these random numbers, and I copy and paste 500 random numbers from 0 and 1. I copy and paste them into the frozen data, and then I generated these beans by an increment of 0.1. So from 0 to 1, 0 to 0.1, 0, 0.1 to 0.2, 0.2, 0.3, 0.3 to 0.4. These are, we call them beans. So we want to see the frequency of the numbers that are in each beans. Okay, so we have 10 beans here, as you can see here. These are our beans. 0.1, 0.2, 0.3, so on and so forth. And then this, what we did here using the data analysis, it actually created for us this table, the frequency table. So for each bean, we counted the number of generated random numbers that are within that bin. So for example, there are 37 numbers within bin 0.1. That means the numbers that are the random numbers that have been generated and they are less than 0.1, there are 37 of them. The numbers that are between 0.1 and 0.2, that means they are bigger than 0.1, but they are less than 0.2, they are 50 of them. 52 are between 0.2 and 0.3, and so on and so forth, as you can see here. Right. So it is not exactly uniform as we want it to be, but it kind of is. So it has to be like a uniform kind of flat shape. But if you generate more, say instead of like 500 that I generated here, if you generate 5,000 or even like more than that, 50,000, it's gonna approach like a flat line. So all of these thick columns here or bars here are gonna become the same height. And that's what we mean by uniform distribution. Okay, so they mean they are equal chance of being selected. Any question?
Can you go over how you made your histogram one more time?
Sure.
Thank you so much.
So I'm gonna delete this. So you go to data tab, the analysis group, you go to data analysis, you open it up and you go to histogram from the left window here. You click OK, and it's going to open up this window for you. Then I'm going to get rid of actually this. I want to put new numbers so you would see what I have done here. Right. So the input range is actually the random numbers that we want to give it. So basically what we want to do in this, using this histogram is, as I said, you want to generate different beans to see what is the frequency of each bean, and also kind of graph that probability distribution based on the beans that they have with the frequency. So in the histogram, if you remember from statistics, it's the frequency graph of your distribution based on the beans that you have defined. So because I have the numbers from here from 0 to 1, I have divide them to 10 beans, 0.1, 0.2, 0.3. You can do whatever you want. It can be like 0.3, 0.6, and then 1. It depends on you, whatever you want to do. So I have defined these beans here. Now I want to graph the histogram of that. So I open up the data analysis tab, I go here, and then here I'm gonna put all my data. So the input range is where your data is. I want them to be here. So that's B11 to the last number, which was B51. So that's B11 to B510. When you do that, it automatically is going to use the absolute value for that. Right. And for the bin range, these are my bin range. You can just select them, or you can put them there. I don't need labels here. You can actually produce the histogram in a new worksheet, or you can use it like just produce it here, print it out here. So I wanted it to be here. So it is going to ask you what's the left upper corner of the output range should be. So I want it to be here, for example. And make sure that you put the chart output. It has other options that you can see here, the cumulative percentage, the Pareto, and others, but we don't need them right now. So I'm going to now generate the histogram and the frequency. So as you can see here, it generated the bins for us here, the frequency and the bins. So it says between 0 and 0.1, there are 37 numbers. So out of these 500 numbers, random numbers that I generate, 37 of them are in range of 0 to 0.1. 50 of them are between range of 0.1 and 0.2, and so on and so forth. And this is the histogram. So this is the graph, but generally, if you remember from statistics, the bars should be thicker and also they should be closer to each other. So to do that, I kind of modified it. I right click on this and then click on the format data series. Okay, so make sure that you just don't just right click on anywhere on the histogram. You have to click on the bars. Okay, so now the bars are selected. I right click on it and go on the format data series. It's going to open up this for me. The gap width, this is where you can actually say that I want these to be closer to each other and also thicker. Okay, so now it's 150%. That means the gap between them are thicker than the width of each bar, like 150% of it. Right? So I wanted this just to be to 5%. So now it's thicker. And I don't really need this label, so I'm going to get rid of this. And this is the frequency table that I have. If I generate different number, I'm going to copy them here. We're going to get a different one. It's going to override this. So it's going to be like this.
Thank you so much.
Sure. 5, 4. So as you can see here, but this is the same thing. It didn't generate any more. Well, anyway, you got the idea. All right, so let's move on to the next one. So that was the uniform distribution. How we do with time? Okay, we're good. So please let me know if I went over time. Let me know if you want to take a break. I mean, I want to. So that was the uniform from 0 and 1. What if you want to generate samples for the uniform distribution of the between A and B? That means the lower cap, or the minimum of A and the maximum of B. So the formula is easy. That's A plus B minus A multiplied by rand function. That's going to, you don't need a new formula for that, for the uniform of A and B. You can just use A plus B minus A multiplied by rand function. It's going to generate a uniform distribution from A to B. Okay. Right. So suppose that we want to do the same thing. So we want to actually generate 500 random numbers for the uniform distribution of minimum of 3 and maximum of 10. Okay. So let me see if I have used rename this. Yes. Okay. So this is A and B. These are my inputs. So I'm going to use the input theme here, or style for them. So minimum is going to be 3, maximum is going to be 10. And I want to generate 500 of these. How should I do that? But I'm going to use the rand function, but I'm going to use the formula here. So that's the formula is A, the minimum, plus B minus A, which is the length between B and A, multiplied by the rand function. So this is going to be A plus B minus A that multiplied by the rand function. If I click enter, it's going to generate a number between 3 and 10. So that's 9.13. Right? So let me actually generate 500 of these. So I'm just going to drag this down to 5.10. 510. Too far. Okay, that's 500 numbers. If you click again here, it's going to generate new numbers, all new numbers. All of them are going to change. But if you look at them, all of them are between 3 and 10. Right? 3 and 10. So I'm going to copy them and then paste them in the second column to make them froze, not change. And to do that, I'm gonna paste them as values only. So just to make them cleaner, look cleaner. I'm gonna make them center. And these are the bins that I want to use. 3, 4, 5, 6, 7, 8, 9, and 10. So increment of 1, starting with 3, and ending with 10 maximum. So I'm gonna do the same. I'm gonna use the data analysis and plot the histogram for this. So this is still active for the other sheet. I have to change it. Right. So this is B15 this time. So because this is B15, so I had to go actually it's more. So I had to go to 514. Actually, 514. 514. So now they are 500 numbers. Exactly. Values, now they are fixed. And now I can do the histogram. No. 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 All right. So the inputs are B15 and B514. 14. That's
Professor, can I ask a question?
yes.
The frozen data, what exactly is that? Because when you copy and pasted it over, I saw the numbers change. So is it just
I just wanted to generate, it doesn't matter. I mean, we are not working like, with real numbers. These are just random numbers. So because they done like, whenever I actually paste or touch anything here, it's going to regenerate new numbers. So it's kind of difficult to stop it. And to stop that, that's why I actually have to paste it somewhere else to make them stop regenerating, right? So I paste them as values, not the function. So that's the whole point, because I want the values to stay the same. So right now, if you see the frozen data here, these never going to change, no matter what I do. So no matter whatever I do here, they're not going to change. But for these, they're going to change. All of them are going to change. But because I want this value, I wanted a set of value that both of us can see, I needed to make them stop to regenerate, right? So that's the whole idea of having a solid data that they are not changing, right? So that's why I pasted them as values here, so you can see them, right? So now the analysis that I do here are for these solid values that don't change. I don't care about these values anymore, right? The column A, you can forget about them right now. Right now, my data is actually at A. Okay, so.
Okay, and then that makes sense. And then when you copied them over, was it just could like actual copy and then paste. It didn't copy the formulas. It just took the numbers.
Yes, because I did for on high. When you paste them, you can go with it. You get different options. One of them is it has a preface of 1, 2, 3, and it says values. So if you click that option, it's going to will only paste the values and not the function, which is the rand function. Otherwise, there are different options that the function can also be pasted. So when you just paste the numbers are going to be the same. It's not going to change anymore.
Okay, yeah, that's good to know. I have seen the different paste options that you're talking about. I just never knew necessarily the difference. Thank you.
Yes, yeah. So the one that has 1, 2, 3, let me copy this here so you can see. So if you click on this, you get different options here, right? So one of them is 1, 2, 3. This says values in this here, right? So it says values. If you use this, if you paste them as values, the value is going to be the only one to be pasted here. This one is said also number formatting. So whatever number formatting you're copying from, that also is going to be pasted here. For example, if I had used blue theme color, is going to be applied to the paste values as well. But this one as well. This one is going to also show the formatting, the color. This one is only the number formatting, such as the percentage or whatever kind of that use. So each of these are for specific purposes. This one we have worked with. This is going to actually transpose it. Okay, so you can actually copy a column and paste it as a row. We have done this before, right? So if I click on this, it's going to transpose. So we used this before. All right. Everything good? Should I continue?
Yes.
Okay. We're gonna go with data analysis again. I'm not sure where it was. So this has to be 514, and this is these values. I want this to be here. And I'm gonna click OK. No numeric data. B11, oh, that's fine. B15. B15 to B2 and C15. Okay, now it should work. All right. So this is our beans, and this is the frequency numbers here. I can make them center here. Look better. So we have nine actually beans here. One of them is 10, the other one is more. We don't actually have any more than 10, right? So that's why the frequency of more than 10 is 0, right? Also, none of the values generated are 3. That means that none of the values that were generated from the uniform distribution were 0. Okay, but for the rest of them, you can see the distribution. So I can make also this cleaner. And, but anyway, you can see kind of we don't get any numbers oddly here for 3, but we get them for the rest of them, and they are almost flat. But if you generate actually a lot more than 500, say 5,000, you would see 3 probably, and also you get like a more flatter height to these bars as well. So that was for the uniform. Now let's go to discrete. All right, so this is what we have here. This is like an empirical distribution that we have generated. This is similar to what we did in the PowerPoint presentation. So these are the possible outcomes. X is discrete, and it can only take these 4 values. It can either be 10 or 15 or 20 or 25. It can it gets the value 10 by the probability of 10%. I can actually turn this into probability percentages. It can take a value of 15 by probability of 30%, 20 by 40%, and 25 by 20%. So now to kind of be able to generate from sample from this distribution. So this is a made up distribution, right? This is, we just made it up, right? So to be able to make from this distribution, this is what we can do. I have actually built this table myself. It's called lookup table, and the second column shows just the values, possible outcomes. The first column shows almost the cumulative probability distribution, and it starts from 0. It shouldn't start from 0. And the next one is just going to be the previous one plus 10. So this is, for example, for 15, the cumulative probability for 15. That's 0 plus 10%. So that's going to be 10%. Let me actually convert this to percentages as well. Okay. So for 20, it's going to be the previous distribution, the previous probability here, 10 and 10% and 30%, which is 40%. For 25, it's going to be this 40% and that 40%. So it's going to be 80%. You can see also the formula here. Okay. So this is how I have come up with the cumulative probability. Okay, so I start off with 0 here. That's just 0. For the next value here, that's this value here, which is E12 plus C12. Okay. The next one, E14, is equal to E13 and C13. So that's kind of give me the cumulative probability almost. Okay. So now that I have this, I can actually produce actually the sample from this distribution. You can also see the distribution graph here. If we just plot these two, the outcomes and its probabilities. So the y-axis shows the probability, the x-axis shows the outcome. Okay, so for when the outcome is 10, the probability was 10%. So the height of this bar is 10%. Okay? When the for x outcome is equal to 15, the probability was 30%. So the height of this is 50%, 30%, and so on and so forth. So as you can see here, this is kind of an odd shape, and it's skewed to the left. Okay? So we want to generate from this distribution. Okay. All right. So we are almost at the break time. We're going to take a break and we're going to come back and do the rest of this. We're going to sample from discrete distribution and we're going to next do the normal distribution. Okay. The last one is just some instruction, helpful instruction for you to how to work with the histogram. It's not so we only have one more distribution. Then we're going to move on to the next lecture. All right. So we're going to take a break now for about 15 minutes, and then we're going to come back. Okay, so see you in a bit. All right, hello everyone. We are back. Let's work on our spreadsheet. Okay, so we were doing on discrete one. Steam Basics, which one was it? Yeah, this one. Okay. So before the break, we talked about this discrete probability distribution. This is like, a crazy random age probability distribution, and we want to use Excel to sample from this distribution. These are the outcome 10, 15, 20, and 25, and these are the probability of those outcome. And this is actually, you can see the probability distribution graph for this distribution. Okay, how can we sample from this crazy empirical distribution that we have made up? Okay, so we can even do that using Excel. What I have created in the middle to use for my sampling is this table right here. I call it lookup table because I'm going to use this lookup table in my VLOOKUP, generate the random numbers using uniform distribution from 0 and 1, and then find the kind of histogram or frequency table for that. Okay. So this lookup table has two columns. The second column is just the value column that you see here, the 10, 20, 10, 15, 20, 25. The first column is kind of the cumulative probability distribution. It is not exact cumulative probability, is off by one row. And the reason that we have to do that is because the VLOOKUP function needs to start the table, whatever table you're looking for, from 0. So that's why we are kind of a little bit off in this table from the cumulative probability distribution table by a row. So the first start with 0 is just 0. The second for 10, for 15, the value for the cumulative probability is the previous value, as you can see, which is E12, and the probability of previous one, which is 10%. For the next one is the same. It's going to be the probability of 15 plus the cumulative probability of 15. So we're going to get this value of 0, 10%, 40%, and 8%. Okay, now say that I want to generate a sample from this. So we're going to use the VLOOKUP function. Okay, so as you can see here, VLOOKUP. The first parameters for VLOOKUP that we have to use here, we're going to use the rand function as we had used before. So rand function is going to generate the probability here, a value between 0 and 1. Okay, so this is, if you remember from the slides, we're going to have to kind of doing the inversing thing. We're going to give it a probability value between 0 and 1, and based on that, we're going to inversely find the x here. Okay, so because we are sampling for it. Okay, so I give it the rand function. Now I'm going to look for the lookup table. Name is lookup table. It's here. This is the table that I have. This is what I have done. I just selected this and named it lookup table. Okay, so from this lookup table, look for the values, kind of match the values of the rand function and the first column, and produce or output the second column. Okay, this has to be 2. So this is what's going to happen. It's going to generate a random function, a random number, say 0.11. Okay, so 0.11 actually is between 10% and 40%. So it's going to output us 15 if it is true. If actually generates 11%, it's not going to generate. It's going to generate a different number. Okay, so it generated 15, as you can see. So as I do that, you can see that it's going to generate different numbers. I mean, we have 4 numbers, so it's either going to be 10, 15, or 20, 10, 15, or 20, or 25. So I can do this actually multiple times. Let me actually do this. Random number. So this is the probability. And here is something. I'm going to say this is rand, or say y. Replication. I'm going to generate 20 numbers here. I'm not 20, I can't do 20. I'm going to have to and now I think we have the chance to produce 20. Yes, 20. Okay, good. So 20. Now I'm going to make this a little bit more visible and easily to read. And then I'm going to copy and paste it to the 20 cells. So as you can see here, I have generated these 20 random numbers between 0 and 1. That's my y value. And now I'm going to use the VLOOKUP function. And the VLOOKUP function is I'm going to give it this value that you can see. And then the lookup table and 2. So it's going to give us that one. Okay. Now I can actually talk with you about this. Let me make this smaller too. Everything is visible now. So for example, the first random number is 32% almost. So 32% is between 10% and 40%. So the VLOOKUP function is going to come to this lookup table. It's going to go through the first column, which is the cumulative probability, and it's going to compare and kind of see the probability that we created with the rand function, y. It's going to see between which value it is, and it's going to give us the corresponding previous value. For example, 32% is between 10% and 40%. So it's close to, it has to be 50. It's 15. So it's going to generate 15 for us. Okay. So the next one is 11 or about 12%. Okay. So it's going to 12% again is between 10% and 40%. It's going to give us 15. Next, for example, 89% is more than 80%. So it's going to give us 25. So it's 25. 84%, again, greater than 80%, is going to give us 20. Right. So this is how we have generated or sampled from this. Okay. Any question? So as you see here, this is not that difficult either. So using this lookup table and cumulative probability that we build up here, we can even sample from a made up empirical distribution. All right, so let's go to the last one, normal distribution. So normal distribution, you're familiar with it, is also called the bell curve distribution or bell-shaped distribution. It's the most common and popular distribution. It has two parameters, the average and it's the standard deviation. So this is what we want to do. We want to sample 500, generate 500 numbers using from normal distribution. Okay, so this is what we have here. These are our input. I'm going to make them as my input kind of theme or sign. So the distribution, normal distribution, has an average of 100 and a standard deviation of 10. You want to generate 500 numbers from them. And I have here the number of observations, so 500 here. And then the observation, which is my random number, my sample. And then I'm going to copy and paste it to make it frozen and then using the data table to generate a histogram for you. Okay, so let's see first how we can sample from a normal distribution. So the normal distribution that you want to sample from, you need to have the two parameters. Here we have the mean is 100 and the standard deviation is 10. I think I have named this, I'm not sure. Let me see. Yes, mean and standard deviation, they are named. So the formula here, again, is kind of the same. You're going to generate a y, which is the probability using the uniform, using the rand function. It's going to generate the value between 0 and 1, and that's going to be our probability. And then you're going to use the norm.inv, the inverse, and give it also the rand, the probability, the minimum, and the standard deviation is going to give us the x for us, the sample. So this is how we sample from. So this is going to be norm.inv. The probability, I'm going to just use rand. And the mean is going to be constant value, and the standard deviation is going to be constant value. Right. So that's one value, 19.62. So now I'm going to generate 500 of these. Then I'm going to copy and paste it here to make it frozen. Right. So 1, 2, 3 values. If I click on this, it's going to be pasted as values only. So as you can see here, because I only pasted as values, the style which was 2 decimal from the where I copied from column B were not copied. The 2 decimal style were not copied into my destination column C. Okay. If I paste it as using the format as well, it's going to be pasted with the 2 decimal point as well. Okay, so that's the kind of difference between the two options. All right. Anyway, now you can see that these numbers change, but my frozen column doesn't change. Right. All right. Anyway, so because my average is 100, I want to build up a histogram for these bins. My bins are 70, 75, 80, 85, up to 125. So about 30% below the average and 30% above the average. I want to generate the histogram for. So let's do that. So by now you should have a good grip on how to build a histogram based on a distribution. Because this is the same worksheet that I have used before in different tabs, in different actually pages or sheets to generate histogram. When you open up at different sheets, you open up the data analysis table, histogram is going to have your previous values in it. So you have to make them clear them all. I'm not sure if this must be also true in Mac, but I'm not too sure about that one. So that's 21. So that's C21 up to C520. And my bin range are in the E column. And I wanted this to be produced here. And I want the chart output to be generated for me. All right, here we go. These are the bins. And this is my histogram. This is very interesting. As you can see here, kind of look like the bell cave, the bell shape that we talked about. So I'm going to make this smaller. Okay, it looks like almost look like a very symmetric normal distribution, right? And if you generate more than 500, say 5,000 or 10,000, it's going to be better look like to a bell curve bell-shaped distribution. All right, so that was about sampling. So let's go to the next lecture. So we're done with part 1. I'm going to open up part 2. Right, everyone sees this PowerPoint?
Yeah, we can see it.
Okay, so this is part 2 from our introduction to simulation. We're going to see an application. This is like kind of a silly application, but I think it's interesting. It's an interesting application, but you know, it kind of cool too. But this is not kind of application that you want to do with simulation. But I just wanted to show you that even for a kind of curiosity question or kind of probabilistic or mathematical type of question, everyday question, you can actually use simulation to answer this question. So assume that you're at a party that there are 30 people in it, including yourself. You may be wondering, if you're really kind of a math nerd, like I am, you would maybe wondering, what is the probability or the likelihood that at least 2 persons have been born in the same day, but they have the same probability? That means not the year, the day. Okay, so we have 365 days. So considering the month and the days, you may be wondering, okay, what is the probability that at least 2 people here are born in the same day? You know, they have the same birthday, for example, right? Well, if you remember from a statistic, there are analytical ways to do that. But here I'm going to show you actually you can answer kind of this interesting question with simulation as well. Okay, so use probability theory and solve analytically. Second one is go to lots of parties and ask everyone their birthdays. So you have to go to a lot of parties to get a good estimation of that, not just like, you know, 5, 10. And the last one, we're going to use simulation to do this. Okay. All right, so this is what we are going to do. We are going to have to generate for 30 people their birthdays. And because we assume that people are random, we don't know the people at the party per se. So we don't know their birthday in advance, right? So they're random, right? So that means their birthday can be any day, right? So we have to generate for 30 people, 30 different birthdays, okay? So that's a value between 1 and 365 days. There is actually a function in Excel that can generate uniform distribution for discrete distribution between A and B. That's called rand between, as you can see it here, rand between. So this is going to generate uniform discrete distribution between A and B. So that's going to be rand between 1 and 365. It's going to generate a value between 1 and 365. We're going to generate this 30 times. That means for 30 people. And then you have, you know, it's kind of simulating the people in the party and their birthday. That's all of what matters for us, right? Their birthday matter. And because this is kind of simulation, so if you remember from the previous lecture, we kind of have to do to be able to estimate the uncertainty, you kind of have to do the experiment multiple times. Say, as you remember from the previous try that we did in Excel, like 500 times or more than that. So that means it kind of mimicking the idea that you have attended 500 parties of 30 people, and you have asked their birthdays, and you have write them down, and then you're going to come up with your estimation of the probability or the likelihood. All right. So I'm going to show you how we can do this. All right, so this is, we don't need this. We're going to go back to Excel. If you are following with me, you can actually download and open up the birthday problem. Well, actually, the version, that's the done version. And okay, so I'm going to open up a new one. Right. So this is just a new one. I'm going to do it here. So there are certain inputs that we need. I'm going to write it here. First of all, I'm going to follow up my conventions and name this. This is birthday model. And name the sheets, and then I'm going to write the model again. So that's birthday. Whatever the problem is, I'm going to make this a little bit larger so you can see it now. We're going to have to come up with the inputs that we need. What we need, the number of replication, we need that. So that's the number of replication, number of match. That means the number of matches is, suppose that you have asked someone's birthday, you want to see which one from that party also match that person. Right? This is how you find two persons that have match birthday. Okay, so number of match. Okay, this is actually a no match at all. And then the matches, number of matches. As you can see from my computation later on, it's easier to find the number of non-matches. And then from that, because they're complement to each other, we can find the number of matches. And then we can find the probability of matches. So suppose that we want to run the experiment 500 times. And so let's now do the experiment. So we need to generate, for 30 people, we need to generate 30 random numbers for their birthdays using rand between 1 and 365. Okay, so let's see. So this is replication, and this is the mode. 1, 2, 3, 4, up to 500. Okay, so 500 replication, and this is what I need to do. I need to do this for 3 people, 30 people, 2, 3, 30 random numbers. As you can see here, they don't are not visible in one sheet here. So I'm going to make these smaller, all of these. All right. So now they are visible. Okay, so these are people. And I'm going to merge this, make it center, make it a little bit more interesting looking. All right, so these are my people. I have 30 people here now. I have to generate their birthday. Okay, so this is what I can use. Rand between, okay? Rand between 1 and 365. So it generated for me 337. I'm gonna copy this for the 30 people. Now, that's it. I have 30 people's birthday. Okay. So for whether we have a match or not, this is what we can do. We can just find the mode. Okay. So if you remember from statistics, mode is when you have an event happened or occurred multiple times. That's the mode. Okay. So for example, if there are at least 2 people have the same birthdays, then you have a match, and then you have the mode is 2, for example. If you have 3 people that they match, the mode is 3. Okay, so what we are looking for, interested in, is just at least 2 people. So the mode, if the mode is, if there is a mode, that means there is at least 2 people. If there is no mode, that means we have 30 different birthdays. No one is actually matched with another person's birthday. Okay, so when the mode is not available, that means there is no match. Okay, when there is a mode, that means there is a match. So at least 2 people are born in the same day, have the same birthday. Okay, so instead of coming up with any other crazy thing, we're going to use the mode idea, the mode idea. So mode, I'm going to use the traditional mode. It has, as you saw here, it has 2 other options for us. So I'm going to give my 30 numbers to the mode, and it's going to tell me whether I have a mode or not, right? So it said 326, but as you can see here, 326, it's 326. So at least 2 people have the same birthday. Okay, so you can actually generate new numbers to see that it changes. So right now, the mode is 142. Two hundred and 255, 255, 255. I want to make sure that this is correct. Okay, 1 and 365. Okay. Anyway. Oh yeah, so everything looks correct. Because these are random values, I'm going to use the one type that we didn't use before, which was, I don't have it here. Just yes, my rand. So this is like the green theme that we have. That's for randomness. Okay, so that's true because these are random numbers. And now what I need to do is to generate 500 of these. Okay, so what I can do is just copy this. Let me insert that here.
Professor, can I ask a question?
Yes, sure.
How does Excel handle multiple instances of modes in the same data set? For example, mine has a match on 77 and 14, but it's only showing 77 as a mode. So what does it do when there's multiples?
There is another function. It's called mult mode. So if you just, let me go back up here. So if you, let me find another, so it's not too, okay. So for example here, so if you just type mode, it has multiple options. Mode dot mult. This is when you have multiple mode. You have to use this function. Okay, if you're like, this doesn't work for me. I mean, we don't need this multiple mode. We just need to know whether at least 2 people have the same birthday. Means there are at least 2 match here. Okay, so for our case, the mode works. But if you are interested in multiple mode, you can go with mode mult.
Thank you so much.
All right, so as you see here, I have generated 500 birthday here with 300 people in it, 30 people in it, and these are the birthdays. All right, so okay, so as you can see here, some of these values are NA. That means there is no mode. There is no match here. Okay. So for example, we don't have to go through this one. There is no 2 people that have the same birthday. That's why there is no match. Okay. So now we're gonna go back here. We have 500 application. Finding the known pattern match is easy because finding the match is is difficult. right? So first, we're going to find the number of non-matches. We have 500 parties. We're going to find the number of parties that they don't have any match. That's the number of NA. So we're going to use the number of the lookup here, or the count. Count. Count if, I think it was, let me see what it was count if, that's right. So count if B10 to B509. Okay. Yes. Okay, so that's my range. And then criteria. The criteria is the number of NA. So NA. I wanted to give me count the number of NAs here. That means the number of non-matches. So there are 159, right? There are 159 non-matches here. Okay, so if you have, if we have gone to 500 parties, and 159 of them, there were no people with the same birthday. That means there isn't no match. That means the rest of them they had a match. So that's C4. Okay. So as you can see here, the number just changed as I told you, because that's part of the functions. Okay. So again, I have to come up with this. So we have gone to 500 parties. There are out of those 500, 140 of them there were no matches, no people with the same birthday, but 360 of them were matches with birthday. So finding the probability of a match is now easy. It would be the number of parties that had a match divided by the number of total parties, which is 100. Okay, so the probability is about 69%, almost. Okay, and this is actually a very good estimation. So if you use probability, your probability knowledge and analytics to compute analytically using the probability function, this probability, you're going to come up with almost the same. That would be 70-something%. So it's close. It's like off by less than 2%. Okay, so that's very good. And if you actually, instead of 500, you replicate it for say 5,000, you're going to get even closer values. All right. So this is going to be our output. Right, great. And if I click anywhere here, these values are going to change and the probability is going to change. But it's going to stay around 70%. Right? Right. Great. Any question? All right. No question? Okay. So this is what I did. I'm going to so suppose that instead of like doing this, what I did here, we can actually also use, if you remember, the one-way table function that we haven't worked with, not the solver table, the one-way table that we used to do it a couple of weeks back. We can use that instead of like copying and pasting 30 numbers for 500 rows. We can use the one-way table to do that. So what we need to do is the 30 people's birthday, which I have it here. So one replication is enough. And what I need to do is to reference this cell to the mode here. And now I'm going to get rid of this. Right, so that means, okay, we have only done one sample experiment. Now we can actually ask the one-day table to repeat this experiment 500 times for us. Okay, so this is how we can do it. I'm going to grab from this cell here, which is empty, and the next cell, which is I have references to the mode here, and I'm going to select all these cells, the table. Then I'm going to go to the data, the volume analysis. It has been a while. Might have forgot where it was. Data table. Then come here. We have a row input cell. We're gonna leave it alone where it is. We don't have any input cell. For the column input, there is actually nothing that you need to input it here. So what you need is actually kind of refreshing these cells, which is going to trigger or regenerate random numbers each time that is this function is going to be called. Okay, so I have selected for 500. The number of rows in this table that I have selected here is 500. So that means it's going to retrigger this sampling 500 times. Okay, so that's all we need to do. There is nothing to input it. So instead for doing that, there is actually a smart way to do that. So I'm going to go to the column input cell, and I'm going to select at any blank space cell anywhere, a blank space. And if I click OK now, because it's going to click on that space, so it's kind of going to trigger this random function. Is going to kind of, because as I said, the function is dynamic, so it's kind of is going to retrigger them 500 times to regenerate 500 numbers. Okay, and as you can see here, it did it. So it did 500 times. It ran this, and it came up with these numbers. So we have generated like 500 parties again, and the numbers, as you can see here, are updated as well, and our probability is about 71%. It's close to what we had before. Okay, so that was also interesting. We used simulation to estimate the probability of a party of 30 people, and the probability that at least 12 of them have the same birthday. Okay, any question? So let's move on to next lecture. Let me close this. All right. For the third part of the lecture, let me open it up. So we're going to see another example. This is kind of a finance example. Part 3. Walton bookstore model. Here we want to solve a profit model based on our order. So there is a demand for, say, a calendar or book or whatever that we produce, and but we don't know the demand in the market. The demand is uncertain. The demand is a stochastic, so it varies, right? We suppose that we know the distribution of that, and based on that, we can kind of tune our how many should we produce to be able to make the maximum profit, knowing that if we produce more than the demand, that's kind of waste of our money because we can't sell them, and it has cost us to produce them. We may be able to get some refund for, not throw them away, kind of salvage them, but it's going to be less than the profit that we could make by selling them, and it's going to be less than what it cost. So that's not kind of ideal, right? So we want to find the best number of production or number of order that we can have, not knowing the demand because the demand is uncertain, but kind of knowing based on historical data and knowing the distribution. This is what we want to do. So the goal is what order quantity for next year's calendars maximizes the expected profit. Calendar demand is uncertain, and then can be represented by its probability distribution. We assume that each calendar is going to cost $7.50 and sell for $30. The calendars that are not sold, they can be refunded, get a partial refund of $2.50. So this is our approach. We're gonna fix the order quantity to whatever. That's our decision. Okay, it's fixed. We have to order a number of calendars, right? 200, 150, 300, whatever number, right? So our order is our decision, but we don't know about the demand in the market. That's uncertain. So because it's uncertain, we're gonna use simulation to solve this problem. Okay, so because it's a simulation and we kind of have to estimate the demand's uncertainty, we have to replicate the experiment multiple times to be able to get a good estimation of the reality. Okay, so say we're gonna do 1,000 replication or 500 as we did before. So just a heads up, these are the functions that we're going to use for demand, because we're going to generate the sampling based on the information that we have, the probability distribution. We're going to use the VLOOKUP function as we did it for another example here. So VLOOKUP function, we're going to produce random numbers using probability distribution function rand, and then lookup table, and then produce what sample should it be. The revenue is just multiplying whatever we can actually sell. That means based on the demand and what we have, multiplied by the unit price. So because the demand is uncertain, it can be bigger than our, it can be larger than our order. That means whatever we have in hand to sell them, or it can be actually smaller, right? So if it's larger, then we can at most sell whatever we have in hand, right? And the rest of them are going to be unsatisfied demand. If we produce more than the demand, then we can only sell as much as the demand, and then the order that we have in hand minus the demand is going to be unsold, and we can get a refund for that. So that's the revenue. That's why we use the minimum of demand and order quantity. The cost is going to be fixed because it's going to be how many the order quantity multiplied by the unit cost. The refund is going to be the units that we get for refund, which is $200.50 multiplied by whatever is left and unsold, which is going to be maximum of order quantity minus demand. Okay, so if because order quantity can be either greater than demand or less than demand, or it can be equal to demand. If it's actually less than or equal to demand, then we don't have any leftovers, so it's going to be zero refund. If we have more than that, then it's going to be the difference between order quantity and demand. That's why we use the maximum of order quantity minus demand and zero. Okay, multiply by this value by the unit refund, which is $2.50, and we get the refund money. The profit is just going to be revenue minus cost plus refund. So we're going to have to, because we have uncertainty of demand, we're going to do several replication to come up with different demand scenarios and different profits. And then out of these so many replications, say 1,000, we're going to use the average to find the average of the profit that we can make, and that's going to be the average profit. And then we can do actually analysis on how much should be our order so that our profit is maximum. Okay. So we can compute the average profit, the standard deviation of profit, the standard error, and then we can actually also come up with a confidence interval for the demand. So if you remember the confidence interval, we had point estimates and we had confidence interval. A point estimate is just one number that estimates something. So for example, I don't know the average age of my student in a class. Okay, so well, let's go with another big example, like we have a population. So assume that I don't know the average age of people in Santa Clara or San Francisco. I don't want to count all of them. So what I do is I take a sample, and then based on that sample, I find the average of, that means a group of people randomly selected, and I ask them the age, and then I calculate the average of that sample. Okay, so that number, which is going to be one number, average age of that sample, is going to be my estimation of the whole population of San Francisco's age group. So it's called a point estimate. So point estimate can either be correct or can be incorrect, right? So that's why it's usually more likely is wrong. Actually, it can be close, but it's almost never actually equal to the population average. Okay? So a better way actually approach this, if you remember from statistics, is to use the confidence interval. Okay, so confidence interval is going to give you not just 1 point; it's going to give you an interval, and it's going to also give you a confidence level, which is say 95%, and I'm 95% confident that the average age of San Franciscoians are between, say, 35 and 63, something like that. Okay? So it's going to give you not just one number, a range of number, and also it's going to give you a confidence. So that's much better. So this is what we're going to do. We're going to, instead of coming up with an average estimation of the profit that we can make, we're going to come up with the confidence interval. So to build a confidence interval, we need the sample mean plus minus the z-value or t-value. For larger replication, we can use the z-value multiplied by a standard error of the sample. So if you don't remember any of this, it's fine. I'm giving you the formula here. The standard error for the sample mean is a standard deviation of the sample divided by a square root of n. N is the size of the sample. So if I had 100,000 replication, and it's thousands, and S can be computed using the standard error, standard deviation formula.
Professor, I'm so sorry to interrupt. If you're sharing your screen, we're not seeing your Excel sheet.
Oh, I'm not sharing a screen. I'm sharing a. I'm supposed to share.
Not seeing slides or anything.
Okay, thank you.
Thank you.
Do you see it now?
Yes.
Okay, thank you for letting me know. All right, so this is the confidence interval. So the confidence interval is just the sample average plus minus the z-score or t-score multiplied by the standard error. Okay, so we can find the z-score. It's either for 95%, which is 1.96, or for 99%, or for 90%. So generally, we're going to go with 95%. So the z-score for that is 1.96, if you remember from the statistics, multiplied by the standard error. So the standard error is just a standard deviation of the sample, S, divided by the square root of n, which n is the size of sample. So if you, say, have repeatedly experiment 1,000 times or 500, and it's going to be 1,000 or 500. So a 95% confidence interval is just going to be sample average. Any confidence interval has a lower bound or a lower cap and upper cap or upper bound, okay? A minimum and maximum. What you need to compute is these two values. Then I'm going to say, I am 95% confident that the average age of San Franciscoians are between these two values, the minimum and maximum. Okay, so the minimum, the lower limit, is computed using sample average from minus 1.96 multiplied by the standard error. The maximum is equal to the average plus 1.96 multiplied by the standard error. And what you get is an interval and the confidence interval. So say whatever value your X bar is. And that's going to give you a range. So I'm going to give you the example so you understand it. Generally, we're gonna build almost always 95% confidence interval, and for 95%, the z-score or t-score is actually about 1.96. But you can see for other values, for example, for 90% is 1.64, and for 99% is 2.576. As the level of confidence goes up, the range gets wider. Okay, so a 99% confidence interval is wider than a 95% confidence interval, and a 95% confidence interval is larger than a 90% confidence interval. We can also estimate the confidence interval for pi. Pi is actually the proportion. If you are dealing with a variable that is a proportion. For example, you want to see the proportion of or the probability of accident, having a car having an accident, or the proportion of the customers who are satisfied, or the proportion of customers who give a restaurant 5-star, right? So then that value is just a value between 0 and 1, say 20%, 90%, 70%. So that you can actually also build a confidence interval for proportion using the same formula, except that the standard error formula is the square root of p multiplied by 1 minus p, that's the proportion, divided by m. We are not working in this session with this formula, so don't worry about this formula for now, but we're gonna use it maybe later. All right, so let's go to Excel and do this experiment. Okay, let me share this Excel file with you. All right, so this is the data file, and that's all we need to do the experiment. Open up the full complete done version as well, so I know what I'm doing. All right, so we have the inputs. One of the inputs is the unit cost. We need a unit cost. So that means every calendar is going to cost us $7.50. We can sell the calendar for $10, and the refund is $2.50. Our order quantity is a decision variable, so that's why we use the kind of pinky color. And this demand distribution, because we said that demand is uncertain. Okay, so when we said that demand is uncertain, based on the previous historic data, we may be able to kind of guess the probability distribution. So assume that this is the probability distribution that we have from this. It could be anything else. It could be, for example, following generally a normal distribution, and then we may have to sample from a normal distribution. So right now, our demand follows this distribution here. This is the distribution. It gets values between 100 and 300. It gets a value of 100 by 30%, 150 by 20%, and 200 by 30%, 250 by 15%, and 300 by 0.05% or 5%. Okay. So how should we approach this? Because the demand is uncertain, we know that this is the probability distribution. We need to generate a sample of this demand, and we're going to repeat that a number of times, say 1,000. And for each of them, we're going to find the profit. So we're going to have profit for 1,000 experiments. And then we can find the average profit for all those scenarios and the standard deviation of that. And that's going to be, that's going to be our point estimate. And based on those, we can actually build a confidence interval, right? So let's do that. So I'm going to kind of write here, simulation model. And this is going to be my replication. And here are going to be the data that I have, which is I need the demand, I need revenue, I need cost, I need refund, and I need profit. So I'm gonna make this center a little better. My replication is going to do this 1000 times. The demand is uncertain, so we have to generate that. So to be able to do that, I need to use the summary table. Use the cumulative, remember. And the rest of them are just can be computed based on the demand and also how much we have to produce. For example, the cost can be is just, let me make sure that these are named. Formulas, page names, we don't have any names here, so I'm going to name these and these. I'm gonna name this. So for example, the cost can be how much we order multiplied by the unit cost. The refund is going to be my refund money multiplied by the maximum of whatever I have ordered minus demand. So demand right now is 0. I'm going to generate that. And revenue is just going to be the unit price multiplied by how much I can sell, which is going to be minimum of demand and order quantity. And the profit is just going to be revenue plus refund minus the cost. Okay. So I have everything here, except that I have to generate the demand. And demand is going to be a random number. So everything is good. Now let's go ahead and generate the demand. So lookup table, and this is going to be cumulative probability. And here I'm going to outcomes. So this is 100. Zero. This was this. Okay, so I'm gonna call this lookup table. And here I'm going to generate that. The V lookup value is going to be rand. And the table is going to be lookup table. And the second output, the second column, it's going to give me back. So right now it's, for example, 100. If I want to just test this to see, it's 200. Okay, so it looks like that it works. This is my random variable. Actually, all of these are randoms except the cost. So I'm going to make this Profit is also random because it depends on demand as well. Profit is random. Refund is also random. Except cost, everything is random. Cost is not random. Okay. So 1,000 and yes. So this is what we have. I have generated 1,000 demand, sampling demand, and then computed the revenue, the cost. The cost, as you see here, is constant because it just depends on this fixed value, which is the order quantity and the unit cost. So that's why the cost doesn't change, right? But any other value that was shown by green color did change, right? And as you can see here, the profit can get different values here. So we're gonna have to find the statistics for that. So I'm gonna do it here, say here. So here I'm gonna go with the average profit. Standard deviation of profit and standard error, and then 95% confidence interval upper, 95% confidence interval lower. So the average is just going to be let me name all of this. Do I need not only need the demand and profit? So I'm going to name this profit. Okay. So that's the average of profit. So the average of profit is 148. You can see here that actually when the demand can be 100, 150, 200, 250, and 300. When demand is 150, the profit is 125 based on our order quantity is 200. When the demand is 100, we actually lose money. So we don't make any profit, we actually lose money. When the demand is 250, we make 375, and so on and so forth. So, but the average profit, if we order 200, our average profit is 148. The standard deviation of profit. So that's STD .s. It has two options, .p and .s. .p is for population, .s for sample. Because this is a sample, we're going to go with .s. So .s, I'm going to get the profit here. So that's the standard deviation to get rid of these decimal points. And the standard error is just the standard profit divided by a square root of n. So that's the SQRT. N is 1,000. 1,000. And I'm going to make this clear too. So now we have the confidence interval. So the confidence interval upper level is the average plus 1.96 multiplied by the standard error. And the lower confidence interval level is the average minus 1.96 multiplied by the standard error. To make those edges. Okay, so let's use the output for this. All right. So this is the 95% confidence interval for the profit. We are 95% confidence that the profit is going to be something between $156 and $194, right? And that's based on 1,000 experiments and assuming that the other quantity is 200. So if I change this, so instead of 200, if I go with 250, these are going to change. 200, say 180 is going to change. 150. So you can do what if analysis. You can run actually a standard that one-way table on this based on different scenarios. So you can also optimize the activities, right? So this is going to be your decision variable, and you have to maximize the minimum profit, for example. All right. Anyway, we are almost done, I think. Yes, we are done. We are done, and that will be our introduction to simulation. Hope you enjoyed it. As you saw here, it's a totally new topic, new subject. It's simulation. It's work with uncertainty. We are not optimizing anything, but we are studying an uncertain stochastic system, and we are studying its performance based on different attributes or parameters that it has, an average, standard deviation, whatever. Okay. Any question? All right. Thank you very much, everyone. Have a great night and have a great weekend. See you next week.
Thank you,
Thank you, Professor.